All right, we'll get started. I think we might have a couple people still straggling their way in. Today, we are going to go through 2.2, so please have that out as we kind of get started here. A couple things of note, your tests are graded. I have not released those scores or the answer key for that just yet, but I have graded that thing, and I'll probably be opening that up tomorrow morning. With that, I'll give you a little bit of a rundown. There were a couple technical issues for a couple students, but it seemed like in general, I still haven't heard a ton of negative things in terms of access and formatting of questions or anything like that. So I'm safely assuming, I hope, that formatting hasn't screwed anyone up or screwed up anyone's grade. My plan is to have a retake test available on It's Learning, and I'm just going to leave it open. You'll get one retake attempt if you so choose. And the way that retake will work is you're only allowed to take it if you got less than 70% on the test. So this is similar to last year. Last year in chem, right, you only were required to retake it if you got less than 75%, if that rings a bell. And then, you know, prior to us obviously shutting down in the spring, or, well, I guess whatever you want to call it, the idea with regular chem is that you were required to retake all of your quizzes until you passed them all with a 75. My retake policy is different. Okay, so for AP chemistry, and I'll kind of communicate this policy again and again, hopefully to you guys so you understand it, but my retake policy is going to be this. If you get less than 70, which in my class is like middle C, okay, because if you do remember from day one, my grading scale is different. 85% in this class is an A, 75% is a B, 65% is a C, and so on and so forth. Okay, so if you get less than 75%, I'm sorry, screwing it up. If you get less than 70%, you're allowed a retake. Your retake is rolled in or averaged with your original score. All right, so my plan is to open that retake up tomorrow and just let it sit there. And if you guys take it, or if you need to take it, if you want to take it, I'll just periodically check and see if anyone has done it, and then I'll fix your score in the grade book as needed. Okay. Yeah, I mean, the scores were not too bad. They were okay. There were some really, really good. There was some really not so good. But I have a hunch if you felt confident going in, you probably did well. If you did not feel so confident going in, you probably did not do so well. I'm hoping there's not too many surprises tomorrow. Fear not, if it didn't go the best, again, there's a retake available for you, and I would strongly recommend that you know, put the time in and make sure that you understand and try to relearn some topics and rewatch some videos and get ready for it. What else did I have? Oh, the retake. The retake is different than the original test, okay? So be aware of that. It is not the same test. Is it similar? Yeah, it's very similar. Again, I'm not testing different concepts, but I do have different questions on the retake, okay? So do be aware of that, that if you use the original test as like your kind of baseline of what the retake is going to be, it is a different test. Same concepts, similar questions, but typically I'm switching numbers, I'm switching the elements that I'm using in examples and things like that. So it is a different test, just to kind of put you on alert if you are somebody who wants to retake it or needs to retake it, okay? All right, that's all I have for that on right now. Let's get rolling into 2.2. 2.2 is all about intramolecular force and potential energy. So I'll define what intramolecular force is in just a little bit. Let me turn on my smartboard, hold on. There we go. But our objective for today is we want to represent the relationship between potential energy and the distance between atoms based on factors that influence the interaction strength. All right, so we're going to talk about both covalent and ionic bonds today. The first chunk of this, like the first page and a half, is all about covalent. And again, just to kind of redefine those or revisit that topic, covalent bonds are when electrons are shared, okay? You have two atoms and there's a bond between them, and the electrons in that chemical bond are shared between those two atoms. Now, that could be a perfectly even sharing, okay? Maybe we have, like, you know, hydrogen and we have hydrogen gas, H2. The bond between the two hydrogens is perfectly shared. The electrons are equally shared between those two atoms. We call that a non-polar covalent bond. Non-polar is trying to say that there's no charges, okay? It's just perfectly equally symmetrical, and there's no positives or negatives. But then we have examples of polar covalent. A polar covalent bond is when the electrons that are shared are not shared equally. You have chlorine and you have carbon or something, right? And the chlorine is much more electronegative. It has a much higher value of electronegativity. And as a result, the electrons that are shared between those two atoms are pulled towards the more electronegative atom, okay? So covalent bonds are first in this worksheet. Ionic bonds are last. So just to kind of give you a frame of reference. So I have giant paragraphs all over this thing. You're more than welcome to kind of highlight or underline as we go, but I mean, a lot of the notes or a lot of the things that I'm going to verbally say to you guys are kind of in writing too. So just be aware. So understanding the various factors that affect how strong a chemical bond is will help us better understand the properties that different chemicals have. Now, physical properties, right? Like macroscopic properties, for example, like, you know, why is this table hard, right? If I knock on that table, why is it rigid, okay? A lot of the properties that we experience in our macroscopic world, right, the big world, are a result of the strength or the interactions of very, very tiny atoms and ions and molecules, okay? So these properties that we're going to look at directly correlate to what we experience in the real world, right? Why is water liquid at room temperature, okay? And other substances, why are they solid at room temperature? And why are gases gases? And all of these different property things, right? There's all these kind of questions that's like, you know, well, why does that make sense? Or does that make sense? And a lot of that has to do with the types of bonds that these molecules or these atoms have. And that kind of influences the types of properties that we see. So since covalent ionic bonds are unique from one another, we have to analyze the strengths of these bonds differently. So be aware, we're starting with covalent, okay? Covalent is the whole entire front side and the top half of the back side. So this is all covalent to start today. And then when I say at the bottom here, when I talk about a bond being stronger, what I'm really trying to say is that it requires more energy to break that, okay? This will come up later in the year as well, but I'll write it right now. Okay. If you want to break a bond, you need energy. Whenever a chemical bond is broken, energy is required, always. And this is a misconception, okay? Oftentimes, students will think it's the exact opposite. Breaking chemical bonds always requires energy, every single time. So when I say something is stronger, what I'm really trying to say is that that bond, or whatever we're looking at, requires more energy to break. Okay. All right. So let's define intramolecular force. Please be careful with the way you say that. Intra, R-A, I-N-T-R-A. There are also intermolecular forces, I-N-T-E-R. The entire third unit is on intermolecular forces. It is a massive unit. It's the biggest unit we have all year long. Okay. So please be aware that when you're saying this term, you're being careful with your R and your inflection, I guess. So an intramolecular force, these are the forces within a molecule. Okay. More specifically, and also known as, AKA, these are chemical bonds, okay? When I talk about intramolecular force, I'm describing the forces that hold a molecule together. And the forces that are holding our molecules together are bonds, either covalent or ionic, all right? And by the way, I'm sure you saw, or hopefully you saw, but please type here in the chat if you have not. Just making sure everybody's still here. I'm my Chromebook working today because it, doesn't work. So I'm ignoring that thing for a while. All right, so Covalent bonds. The strength of covalent bonds is going to depend upon a couple of factors. Things like the length of the bond, in other words, how far apart the two atoms are, and the order of the bond. And order is going to be really, really simple. We'll talk about that in just a little bit. Can greatly affect the amount of energy in the chemical bond, or the amount of energy required to break a bond. So below, I have a graph. This is a graph of potential energy versus the distance between the atoms as they are either forming or breaking a bond, okay? So again, there's nothing really to write here, but hang with me as I kind of walk through this explanation. So I have these 4 pictures up top, 1, 2, 3, 4, all right? Picture number 1. This is showing 2 atoms. So these blue little circles here with the black dot in the middle, the black dot is your nucleus, right? The blue around that is kind of trying to represent the electrons in their orbitals. So I have atom number 1, I have atom number 2, and they're really far apart. Okay, in picture number 1, they are so far apart that you'll notice that my line, my red line here, is representing potential energy, okay? As potential energy goes negative, and I have this like double asterisk down here, or I suppose if there was more than one, would that be asterisks? I don't know, that sounds complicated. I don't teach English. Asterisks, let's go with that. A negative potential energy, okay, when this red line on my graph dips below 0, a negative potential energy represents an attractive force between our atoms. So you'll notice that in spot number 1, or example number 1, when the atoms are really, really far apart, we are effectively at 0 potential energy. In other words, they're so far apart, there's no attractive force between them. It doesn't exist. Now, if I move them a little closer together in picture number 2, I move my atoms a little closer, and now we'll see our graph start to dip down. Okay, there's the 2 right here that's representing that picture. Now they're close enough where they're starting to feel an attractive force to one another. The positive charges and the negative charges in both of these atoms are starting to be attracted to the positives and negatives of the other atom. And our potential energy is dipping. Okay, that's a good thing. Lower potential energy equals more stable. All right. Now we keep going, and these 2 atoms get closer and closer and closer together. And now we reach spot number 3. Spot number 3 is the very bottom of my potential energy graph. This spot represents when the attractive forces and the repulsive forces between the atoms are perfectly in balance. Okay? This is the spot of the lowest potential energy, also known as the most stability. Okay? This represents the most stable distance between the atoms. And this is the very spot where we would measure the length of this bond. So you'll see in parentheses down here, H2 bond length. So these 2 atoms are representing hydrogen and a hydrogen. If they're very far apart, they have no attractive forces, no repulsive forces. It's effectively 0 as they get further away from one another. I bring them closer together, attractive force starts to form. I bring them closer together yet, and I reach a spot where the potential energy is the most negative, okay, which means the attractive forces are the strongest at this moment. My x-axis is distance, internuclear distance, meaning, you know, how far apart these things are, right? And at the very bottom, this represents the bond length. When the attractive forces are maximized, in other words, when the potential energy is the lowest it can possibly go, that represents the perfect distance of these 2 atoms making a bond. I know this is probably getting a little abstract, but I hope that sort of makes sense. Let's go to the 4th picture. In picture number 4, I've now smooshed the atoms so close together, and yes, smooshed is a very scientific word that doesn't actually get used in science, but you get my point. If we push these too close together, now effectively the nuclei are too tight. They're too close. Positive charges in this nucleus, positive charges in this nucleus, and at a certain distance, those positive charges aren't really repelling one another, or I should say that the attractive forces are very strong and the repulsive forces are very small, so this distance works. But if I bring them closer together, now these repulsive forces start to really push back. And as a result, our potential energy graph starts to swing upward. And you'll notice that if we keep bringing these things closer and closer together, we eventually reach a point where the repulsive forces are so strong that these things would actually physically snap away from one another, okay? So again, this graph is all this is really trying to do for us is to show us how bond length is calculated or observed. Two atoms far apart, no attractive force. Closer together, hey, attractive force is forming. Closer together, awesome. This is the maximum attractive force that we could possibly have between those two atoms. Because if I start going any closer, now my graph starts going upward, which means that I'm creating repulsion between the nuclei. So this is kind of like the Goldilocks spot, so to speak, perfect distance, and then we measure the length of that on the x-axis at that point. All right. This is for covalent bonding. This is not for ionic. Ionic happens completely differently. But for covalent bonding, the length or the distance between two atoms in a bond can be determined by graphing the potential energy versus the distance between those atoms. And again, where the potential energy is the absolute lowest represents the perfect spot, the perfect distance between those atoms. And that's where we would measure our length, which in this case is 74 picometers. Okay, that's really, 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 really small, by the way, if you're not familiar with the prefix pico, which I bet you're not. And I'm not talking about pico de gallo, which isn't spicy enough, in my opinion. I like a spicy salsa. All right, I'm getting weird today. Maybe that's a good thing. This is probably better than my normal droning on. All right, so electrons have negative charges, and the nuclei they surround have a positive charge. We know that. That's old news. When the two particles approach one another, the electron clouds can overlap. When this happens, and when I say electron clouds, right, let's fix that a little bit because we know a little more now. The orbitals can overlap. Let's call those orbitals. I like that better. Hold on. Okay. The orbitals can overlap. When this happens, under certain circumstances, the electrons that are between the two nuclei can be attracted to both nuclei, holding them together. This force of attraction is known as a chemical bond. When the atoms form a bond, they become lower in energy and the system is more stable. Lower potential energy equals more stable, okay? So when bonds form, they are more stable than the two atoms being separate. The energy saved by moving to a more stable state or situation is released as heat. For this reason, bond formation, whenever bonds are created, they release heat. They are exothermic. Conversely, in order to break bonds, you must put energy in. It's an endothermic process. We'll talk about endothermic and exothermic later this year, okay? So here's another picture. Atom 1, atom 2, I smush them, I get them close together, and here's what happens. The two electrons that are gonna form my bond are effectively attracted to both nuclei, okay? The positive nucleus of this one and the positive nucleus of this one are holding these shared electrons in place because they are equally attracted to both. All right, let's talk about bond order. This is the easiest thing I will teach you probably all year long. When the bond order is blank, we have a single bond. When the bond order is 1, that means single bond. When the bond order is 2, that means double bond. And when the bond order is 3, that means, or we now have a triple bond. Yes, very exciting stuff. Pretty abstract for you to wrap your head around. Bond order is as easy as you think it is. If you hear that the bond order is 2, that means it's a double bond, so on and so forth. No more time needed to be spent there, I don't think. All right, so look up the bond energies. Now, this is gonna be a little harder. I'm prepared here, so I'll do it for you. But on last year's periodic table, whether you remember this or not, I'll kind of try to show you. I don't know if you can see it or not, but on the back of last year's periodic table, we had this column way on the left-hand side, and these numbers are representing the energy of all of the different bonds, or a whole bunch of different covalent bonds, okay? So we're gonna look up a single bond, a double bond, and a triple bond between carbon atoms. In other words, carbon-carbon with a single bond, carbon-carbon with a double bond, carbon-carbon with a triple bond. And then we're gonna make a correlation between bond order and bond energy. So First one, carbon, single bond, carbon. This is a dash. That dash is representing a bond or shared electrons, okay? That's not a minus sign. Please be aware of that. So carbon with a single bond to another carbon. The energy of a single bond carbon-carbon is 346. And the unit of that is kilojoules per mole. I don't know if you actually care about that, but we'll write it down. All right, carbon-carbon double bond. Again, not an equal sign. That is not an equal sign. I should probably use, hold on. Bad teacher. There we go. Let's use like an arrow. All right. Carbon-carbon double bond. That is not an equal sign. That is two bonds. Each bond has 2 electrons. So that would be like 4 electrons being shared between 2 carbon atoms. The energy of this is 615 kilojoules per mole. Carbon-carbon triple bond is 812 kilojoules per mole. All right, so what did we learn? Well, as the bond order, in other words, the number of bonds between our atoms, as that goes up, the energy or the bond energy also goes up. It's pretty simple. It's pretty logical too, right? It would be pretty intuitive to think that a triple bond is stronger than a double bond. That makes perfect sense in my head. That feels like it should be stronger, right? So the takeaway here is as bond order increases, I'll just use an up arrow, bond energy increases. They are directly related. One goes up, the other goes up, okay? If you have a double bond, it's stronger than a single bond. If you have a triple bond, it's stronger than a double bond, assuming that you haven't changed the atoms that you're looking at, okay? All right, next one. Now, if you were here, I would totally bust out the atom kits and let you play with atom kits for a little bit, but unfortunately you're not here, so I have to do this for you. But either way, what I would have had you do is make a little model of a single bond carbon. This bond is broken. There we go. That looks a little better. I'd make you a single bond between 2 carbons. If you can see that, if you're looking at my little camera, I'll zoom in maybe. I can't see myself right now, so I have no clue if this is worthless or not. A double bond with 2 carbons. And then a triple bond with 2 carbons. Okay? And all I would have had you do is make a correlation between bond order and bond length. So here's the single bond again. Here's the double bond. Here's the triple bond. And as I hope you can see if your computer or Chromebook is cooperating and mine is showing you a decent picture, as the bond order increases, the length of that bond decreases. Single bonds are longer than double bonds. Double bonds are longer than triple bonds. Oops. So as the bond order goes up, meaning single bond to double bond to triple bond, we expect the bond length, oops, I can't spell, to go down. Okay, so triple bonds are shorter than double bonds. Double bonds are shorter than single bonds. Single bonds are the longest, triple bonds are the shortest. All right, we have now transitioned, and I even have a little title there, so I hope you're hanging with me. All of that stuff, okay, all of the previous 10 slides is all about covalent. So let me just recap a smidge, okay? Breaking bonds always requires energy. When I say that a bond is stronger, what I'm trying to say is that that bond requires more energy to break it, okay? Intramolecular forces are bonds. When I talk about a covalent bond or when I talk about an ionic bond, they are both considered intramolecular forces, the forces within a molecule holding the atoms together. The potential energy of a bond, when it's at its lowest, when the potential energy is the lowest, the bond length can be measured, okay? the length of a bond between two atoms will always be measured at the lowest possible point of potential energy. Blah, blah, blah. Bond order, 1 equals single bond, 2 equals double bond, 3 equals triple bond. Bond order and bond energy, as you go higher in bond order, single to double to triple, the energy goes up, meaning it requires more energy to break this triple bond than it does energy to break this double bond, so on and so forth. And then the last chunk we just talked about, as the bond order goes up, the bond length goes down. A triple bond is shorter than a single bond. Okay, ionic. So to determine the strength of ionic bonds, we have to use something different. We're going to use Coulomb's law. Now, Coulomb's law has been kind of hanging around quite a bit, and it's never really going to go away all year. It's a huge, massive overarching concept. So I'll re-go through the whole darn thing right now on the next slide, but be aware that Coulomb's law, if you're kind of not sure of what I'm talking about yet when I've brought that up, it's not going anywhere. That is a big concept for this class. So, you know, we'll go through it on a weekly basis almost. And then by the time the test rolls around, you'll be good to go on Coulomb's law. So anyway, so the energy of an ionic bond has a special name. It is called lattice energy. Now, the word lattice, I'll talk more about tomorrow. It's not lettuce. It's not, you're not eating a salad, so please don't misspeak on that one either. Lattice is trying to imply that there is a three-dimensional structure involved. And I'll talk more about that tomorrow, okay? So I'll put a pin in that for today. But let's look at two examples of comparing the strength of ionic bonds. So based upon Coulomb's law, let's make a prediction of which of these two ionic compounds would have a greater lattice energy. And when I say greater lattice energy, what I'm really trying to say there is stronger ionic bond, okay? If you ever see the word lattice energy, your brain should think that that means ionic bond strength or the strength of an ionic bond, okay? So lattice energy really is talking about the strength. I'm having issues today. There we go. Okay. Lattice energy is all about the strength of ionic bonds. More lattice energy or a greater lattice energy means stronger ionic bonds. Less lattice energy or weaker lattice energy means weaker ionic bonds. Okay, so lattice energy is all about how strong are those ionic bonds. Okay, so here's our example. We've got sodium chloride and we've got magnesium oxide. Both of these are ionic, and I'm asking us to compare which of these would have stronger intermolecular forces. Okay, so which of these would have stronger attractive forces between the cation and the anion? So here's what we're going to do. We're going to use Coulomb's law. Let me break this in half, all right? On this side of sodium chloride, I have Na1+. That is the cation of that ionic compound. On the other side, I have Cl1-, chloride. That's the anion of that ionic compound. Let's go to magnesium oxide. Magnesium oxide, I have Mg2+. That's the cation of that one. And I have O2-, the anion of that one. So Coulomb's law says this. If the magnitude of charge is bigger, the attractive force is stronger, okay? As the magnitude of charge goes up, the attraction between your ions goes up. So here's the deal. In the first example, I have 1+, 1-. In the second example, I have 2+ and 2-. Based on the first part of Coulomb's law, which of these should have a stronger or a greater lattice energy? And the answer is, it's got to be the magnesium oxide. 2+ is bigger than 1+. 2- is bigger in magnitude than 1 minus. And as a result, the Mg2 plus and the O2 minus should have a stronger attraction between them, which means that the ionic bond or the lattice energy is greater. All right, so let me write that out, okay? So let's see. So MgO is our answer. Okay. Now, why? Because long answer, I'm sorry. So magnesium oxide is or has the greater lattice energy, the stronger ionic bond. The reason is because magnesium is 2 plus, oxygen is 2 minus, and those are essentially just bigger in magnitude. That's all it comes down to. More positive, more negative means stronger attraction. Okay, so I might even write some more, I'm sorry. Bigger magnitude of charge means stronger attractive force, all right? I'm gonna give you a chance to catch up to me if you're not fully writing these down. Make sure everybody gets it. Hey, you're all still here, excellent. I'm sorry, I don't trust that everyone's here sometimes. So that is the first part of Coulomb's law. That's the easy part of Coulomb's law, I think. In other words, if you have to compare one ionic compound versus another ionic compound, and you're trying to figure out which of those has a stronger or a greater lattice energy, meaning which of those has stronger ionic bonds, the first place you want to look is the positive and negative charges. If one of the two examples you're looking at has bigger positive and negative charges, that's the winner. Bigger magnitude of charge equals stronger attractive forces, okay? But let's go to the last one on this problem. Or the last one on this page. This is different. Make a prediction of which of these two would have a greater lattice energy. Explain your thinking. Okay, so in this example, I have sodium chloride. Sodium is 1 plus. Chloride is 1 minus. And I have lithium fluoride. Lithium is 1 plus. And fluorine, or fluoride, is 1 minus. All right, so now what? We have the same exact charge. We have 1 plus, 1 minus, 1 plus, 1 minus. So this is where the second part of Coulomb's law comes into play. Coulomb's law consists of two concepts. The first concept is, as the magnitude of charge goes up, the attractive force goes up. Okay, that's what we saw in the first ionic example. In this example, the magnitude of charge is the exact same in both of these. 1 plus, 1 minus, 1 plus, 1 minus. So that doesn't help us. We have to go to the second part. The second part of Coulomb's law says that as the distance between atoms gets smaller. As two atoms get closer together, the attractive force gets stronger. So now this comes down to which of these pairs can get closer together. And that has to do with size or the radius. Which of these are smaller ions? The one that has smaller ions is going to have greater lattice energy because those ions have a shorter distance between them. Okay, so let's look at this. We're going to compare the cations versus one another, and we're going to compare the anions versus one another. Sodium 1 plus versus lithium 1 plus. Which of those would be smaller? If you're looking at your periodic table, I'm hopeful that you can realize that, okay, well, lithium is higher up on that column, right? As you go down a column, atoms get bigger and bigger and bigger and bigger. It's the opposite across a row, right? That the whole radius conversation when we go across a row is much more confusing and it's counterintuitive. But in a column, lithium is a smaller atom than sodium. So here's the deal. Lithium 1 plus is smaller than sodium 1 plus. Okay? That's a plus. Kind of. There we go. Let's compare the other two. We have chloride and we have fluoride. Same exact reason, just a different example. Fluoride is higher up on that column. Fluoride is a smaller ion than chloride. Again, when comparing two atoms or two ions in the same column or the same family, the higher up on the periodic table it is, the smaller it is. So fluoride, F1 minus, is smaller than chloride. Okay, so that's all well and good, but now we need the conclusion of that thought, right? So this cation is smaller than the other, this anion is smaller than the other, but here's what that leads to, okay? Smaller ions can get closer together. And as a result, and hold on, and okay, smaller ions can get closer together and they experience a stronger attractive force. As the distance goes down between atoms or ions, the strength of the attraction goes up. Shorter distance, stronger attraction, okay? So these two examples are using Coulomb's law to help us identify which ionic compound would have a stronger lattice energy. Now, again, lattice energy means ionic bond strength, okay? So we have to use both parts of Coulomb's law. The first part is, what are the magnitude of those charges? If you have magnitude of charges bigger on one example than the other, you're done. That's it. Bigger charge, stronger attraction, nothing else to even think about. But if you have a comparison where both examples have the exact same magnitude of charge, 1 plus 1 minus, 1 plus 1 minus, now we need to go to the second part of Coulomb's law. And the second part is all about distance. How close or how far apart are these ions? Smaller ions can get closer together, and that would give you a greater or a stronger lattice energy. Okay? All right, that is all I have. Couple things, one more thing before I let you go. Homework topic 1. for Unit 2 is due on Thursday night at midnight. I have a homework assignment already posted for it, so you can post it whenever you'd like. Homework topic 1 is completely from 2.1 and 2.2. So Thursday, Monday, and yesterday's class, those 3 classes, all of that stuff is your topic 1 homework, okay? That's due at Thursday at midnight, just to keep that, or just to let you know. So that's all I have. Have a lovely day. If you have any questions, hang back a little bit, and I'd be happy to answer them. Yeah, other than that, we'll catch you guys tomorrow. See you later.